ATM is the set of strings like that, such that M is a Turing machine and M accepts W. So this is sort of our classic base problem or base language that we've been discussing. And so the input is a description of Turing machine M and some particular input W for M. And this is the language. And we showed by a self-reference argument that ATM is undecidable. Okay. To also prove that ATM is undecidable. Now, as it turns out, my diagonalization was different than the way it's done in the book. So I want to first do it the way it's done in the book, just so it's consistent. The lectures are completely consistent with what's in the book. Okay, so, and then we'll go back to reductions and exploit the whole machinery of reductions to prove that additional problems are undecidable. So now I'm going to focus on this diagonalization argument and do it the way that's in the book. The book's argument goes like this. Well, first of all, we want to enumerate all the Turing machines, MK. Of course, there's an infinite number of them, but we've discussed before that there's an enumeration of them. They're countable. We can think of Turing machines as the descriptions of a Turing machine is just a string over some alphabet, and we can enumerate strings over that alphabet, so therefore we can enumerate the Turing machines. And what the book then considers as input, it restricts to the following kinds of input: a description of M1, a description of M2, and so on, a description of MK, and all the way down. So this enumeration here is the same enumeration as here. They're in the same order, but this is a string which describes M1. This is the string that describes M2, and so on. Whereas this is just an index that says machine M1, and so on. We know that these are orderable because the strings are orderable, but these are the actual strings that describe the particular Turing machines. And then what we want to put in the table, behavior, the behavior of these particular Turing machines on this particular input. So we don't have up here all possible inputs. When I did my diagonalization, I had all possible strings. But now what the book does is just restricts to those particular strings that are encodings of Turing machines. Okay, that's fine. This is enumerable, and you can do that. And so then you can say, well, what does M1 do on this particular input? Well, it either accepts, rejects, or doesn't halt. So accept, maybe on M2 it rejects. On MK it doesn't halt. Okay, and so those are the three possibilities, and this table is filled out with all sorts of doesn't halt. It's all filled out like that, right? Okay, so this is the first table, and maybe I'll call this table T. And then we say, okay, suppose that ATM really is decidable. What does it mean to be decidable? It means that there's some Turing machine which can take in an arbitrary string of this form, where the first part of it is a description of a Turing machine, and the second one, I guess there may be another, I don't know, something like that around it. This usually means the description of. So the description of the Turing machine and then some particular input for it. Okay, and that supposed Turing machine will decide whether Turing machine M accepts W. So we assume ATM is decidable. So there is a Turing machine, I'll call it H, which decides ATM. And H has a table too, which describes its behavior is. So this is the behavior of H on its input. So, but its input I'm going to describe this way. It's, well, when it's given M1 as the first component, and it's given the description of M1, etc., MK as the second component. So this is the behavior of H on input MI, MJ. Okay? So, or maybe it's, anyway, if it's given Turing machine MI and then the description of MJ, so this is what it gets in the first component and what it gets in the second component. Okay? And then what is H supposed to do? H is supposed to decide whether the Turing machine in the first component accepts the string that's in the second component of its input. So wherever this table says accept, this is going to say accept. And wherever that table says reject, this says reject. And when this says doesn't halt, what should this say? What? Reject, right. H is a decider for ATM. ATM is the language consisting of a description of a Turing machine with a particular string. Okay? And it's supposed to accept when M accepts W. And it's supposed to reject when M doesn't accept W. Doesn't accept means either that M rejects or M doesn't halt. Okay? That's what doesn't accept means. So these two possibilities translate to reject. So this table is identical to this table, except in those places where this table has a doesn't halt, this table will have a reject. Okay? So I'll call this table TH. So TH is identical to T, except where T doesn't halt, TH has reject. Okay? So this is a description. On the assumption that ATM is decidable, there has to be a Turing machine H which has this kind of behavior on this kind of input. All right? So now, on the assumption that Turing machine H exists, I'm going to describe another Turing machine that has to exist. Given that H exists, there is another Turing machine, call it D, okay? And D will take in input of the form, oops, it takes in the input of the description of some Turing machine. Okay, maybe I'll subscript I, but anyway, it's i.e. the description of some Turing machine. So it takes an input which is the same form as the input to here, and the same form as here, the same form as these strings, the strings up here and the strings up here. Okay? So it takes in that input. And I want to describe what does D do on input, let's say MI. So to tell you, to describe what D does on each of these possible inputs, the input is a description of a Turing machine, I'm going to say, well, what D does, if it gets M1, is it's going to do the opposite of what H did. Okay? So on that particular input, since H was an accept, D will be a reject. Okay? And okay, TH is identical to T except where T doesn't halt. Let me just do another one down here. Let's say the next one here along the diagonal was a reject. Okay? Then what D will do is accept, and so on, all the way down the diagonal. Okay? So to see what D does on input of that form, or to specify what D does on the input of that form, we reverse the entry of table TH along the diagonal. Of that table. Okay? Now, sort of a thing to pay attention to is that D only gets the description of a machine as its input. Okay? Along here, when we were talking about H, H's input is a particular machine and a description of some other machine. So it can be any pair like that. Description of one machine, MI, let's say, and then the string just describing another machine, MJ. But D only gets the description of a machine. Okay? So D's table, if I wanted to write out a table for the behavior of D, that's just one-dimensional. It's not two-dimensional anymore. Okay? It would be one-dimensional. It would be all of these, okay, and then whatever value was along the diagonal here, but reversed, would be put up there. Okay, so D's behavior, I could write out D M1, M2, M3, etc. And the little piece we did over there, it would be a reject on M1, and then an accept on M2, and so on. We don't know what the rest of it is. So D's table is simpler than H's table. But the point is that if H exists, then certainly D does. We've certainly described what Turing machine D does on inputs of the type that it gets. So if H exists, then D exists. But again, H takes in different kind. It takes in a MI, MJ, and D only takes in a description of a Turing machine. Okay? So H takes in two pieces, M only takes in one. But again, if H exists, then we're certainly describing what D does, how do we know that D exists? Well, D just has within it, if H exists, it just has an H, okay? And when it gets an input of this form, that it forms a Turing machine, it just runs H, and whatever H does, it does the reverse. So if H exists, D exists. Okay. So D is a perfectly good Turing machine, and its input is of this form. All right? Well, back over here, this is the behavior of all possible, or actually all Turing machines. Okay? This is the list of the Turing machines, and this is the input. So in this table, the input is the same as the input to D. Okay? The input to M1 is a description of M1, well, M1 or a description of M2 and so on. So each one of these Turing machines gets input that is of the same form as D. Each of these Turing machines gets input of the same form as D does, i.e. a description of some Turing machine. All right, well, if D is a Turing machine, and this table describes all possible Turing machines, the behavior of all possible Turing machines on inputs of this type, where is D? D must be in here somewhere, because D is a Turing machine. On the assumption that ATM is decidable, we ended up figuring out that D is a Turing machine. This is a table that describes all Turing machines and what they would do on the same kind of input that D gets. So where is D? So you say, okay, it's right here. This is where I think D is. Some particular line, some particular row in this table. All right? So we look along the diagonal of this table, and there's some value. Okay? There's some value there sitting in the diagonal. And what is it? Well, it's either accept, reject, or doesn't halt. But if this is the table for D, if this is the table for D in here, which is the enumeration of all Turing machines and their behaviors on input of this size, that row should be identical to this. Everybody with me on that? This is a description of what D does on the input of that type. Over in that table is a description of what every Turing machine does on input of that type. So this row where I'm claiming D exists, so D must be in the table, this row better be the same as what we said it was over there. Okay? But is it the same? Well, let's say over here we have an accept. So what do we have in that table for D? Well, that table for D is 2 steps away. This accept translated into an accept I just erased the key to the answer, but I think you'll remember. Let's say this is the diagonal here. If that's an accept, what's this value? That's a what? Accept, yeah. And if this is an accept, what is the value over here? It's a reject, because the values along the diagonal, the values in this row come from the values along the diagonal in this table, and they're the opposite. Okay? So if it's an accept here, it's a reject there. So those two rows are not the same. Okay? Now what if this was a reject over here? Then what is the... By the way, since this is D here, this is D here. Okay? Or D here. Along the diagonal, when the row is D, the column is D, since we're enumerating in the same order. So if this is a reject here, then what is it over there? Well, yeah, because this becomes a reject. This is a reject, so this becomes a reject. And so this becomes an accept over there. So in that case, again, you can see that this row, which I claimed is the description of the behaviors of D, is not the same as what D is supposed to be. Okay, let's finish it. What if this is a doesn't accept? Doesn't halt. If this is doesn't halt, what's the value over there in that position?
Shouldn't happen.
Is what?
Shouldn't happen.
Shouldn't happen.
Because H is a decider.
Well, you may be just taking an extra step here, but I want the first step. Yeah. Yeah. If this is a doesn't halt here, it's a reject here. If it's a reject here, it's an accept there. Okay? So each doesn't halt translates to an accept over there. But again, the important point is those aren't the same. Doesn't halt is not the same as accept. Okay? So the behavior of D on that input, D, is different in this row than in what we deduced for the behaviors of D over there. And yeah.
Is it possible to have doesn't halt though and the behavior of D is of T? Or why is it possible?
Okay. You see, the question was, why is it possible for D not to halt? Because over there, D always accepts or rejects. Is that why? Yeah, you're getting to the point of the contradiction. Okay? So we have deduced over here that D must have this behavior, which doesn't even have in it doesn't halt. Okay? On the other hand, we've said, okay, D is a Turing machine, so it's got to be somewhere in this table. And this table has three possible entries. And I'm simply going through those three possible entries to show a contradiction in each case. If the entry here is accept, the entry over there will be reject. So it's a contradiction that these two rows are the same. If the entry here is reject, the entry over there is accept. So again, it's a contradiction that the two rows are the same. If the entry here is doesn't halt, the entry over there is accept, which is again contradicts that these two rows are the same. Okay? So in all three possibilities of what this is, we see that this can't be the row that describes D. But really, this was arbitrarily picked. I mean, we just said D is a Turing machine. Where is it in this table? And I just made this line here. Wherever you say it might be, or somebody else says it, they might say, "Oh no, it's not there. It's here." Well, it's the same argument. I'll just do the same. I'll do the same thing. We'll just be looking at that position instead. So wherever you claim that D can be, the same argument shows that no, that won't be the row for D. So there is no row for D. So D isn't in here, but this is supposed to be the enumeration of all Turing machines. And we know we can enumerate all Turing machines. That's not a supposition that we can now reject. We know we can enumerate Turing machines because Turing machines are just described by strings, and we can enumerate strings. So there is an enumeration of Turing machines that gets all of them. And yet now we have this D in our hands under the assumption that ATM is decidable. Turing machine H exists, which means Turing machine D exists. But then we were arguing where in this table is D. D can't be anywhere in that table, so D doesn't exist, so H doesn't exist, so the language ATM is undecidable. Okay, that is the diagonalization argument that is in the book.